So welcome everybody. Before we will start with the talks, I would like to tell you a couple words about how the idea of Zen of Data Teams was born and why we think it's important. So the idea came to us about half a year ago when we saw that we weren't delivering as much as we potentially could in our data science team. And the reason wasn't that we were lacking of technical skills and knowledge. We saw that much bigger improvement can come if we concentrate on how we manage our projects, how we work together, how we communicate with external teams and clients, and so on. And we started to look for resources on this topic, and we were quite surprised to see how few of those were around. So that's why we are here today to create these resources on our own. ProExpert was very happy to help us out with this effort. So we partnered up with Lift 99, who manages everything here. And also Northstar AI was very happy to help us out, as it has become much more than just organizer of a conference. It has become a community effort to create ecosystem where AI and data science can thrive. And in these events, we want to concentrate on the human aspects and processes in data science projects instead of technical ones, like it's mostly done. We don't want these meetups to be just a regular set of meetups where you quietly listen what others are telling. We want it to be a platform where discussions are encouraged, where ideas can be created, developed, and tested out, and where we can work together to improve the way how we work. So we will have these meetups every other month, but in between we would like to have smaller discussion groups. These are not openly promoted, so if you want to join them, then contact me later today, email me, or join Northstar AI Slack channel, which is another effort to bring community together in more informal environment where we can interactively discuss our job and so on. So let's go on to today's speakers. Both of them have contributed a lot to data science ecosystem, and both of them are organizers of Northstar AI. They both constantly develop new concepts and ideas, and one of those is data is a specification, which Christian Korjus is going to talk about. So Christian is head of data at Starship Technologies, and he is responsible for improving the security and autonomy of these cute robots hundreds of times. He has also sent out 12 patent requests from different companies. He was co-author of bedtime reading about mathematics or Matemaatika õhtutupik. And he played a key role in being the first open source project to replicate DeepMind's Atari playing AI results, which went quite viral. So let's hear what Christian has to say about data is a specification.
Hello, happy to be here. Maybe I should. I think it's on. What about now? Good. Hello. Estonia is indeed unique for our ecosystem that was just mentioned. I was in a podcast a couple of days ago, and they wanted to get out this numerical stuff about Estonia, that we have the highest number of startups or most funding or whatever. I think these numbers are not true. I don't think that we are #1 in Europe or whatever, but we are good. We are comparable to London and Berlin and not far behind from Silicon Valley and Shanghai. But I think there is something unique in here, and the ecosystem itself is unique. And it's somehow that it is not the case in other countries or communities, that companies are respecting each other so much, or that they kind of help each other, maybe because all the founders are from Skype. But still, it is a unique place. Another unique stuff is that it's extremely small. For example, Taivo will be presenting now as well. We used to be together in university when I was doing my PhD. Then we were together in Starship. Then he went to Verif. I hired his brother to Starship. He hired mine to Verif. It's, yeah. Data specification. I should go straight into it, but just a couple of words about Starship before I do it. That's my daughter. She was driving around with a robot. It was made illegal now by Estonian law. You cannot transport humans anymore. We have a vision, and this vision is, I mean, a lot of people hate it, but I probably not in this crowd. There is, if you step back a lot, like 10,000 kilometers, and you look from like a wide lens about the world, then we could think about centuries in forms of transportation that about 200 years ago, the transport of energy was made seamless or automatic, or human was taken out from there. So if you put your light bulb in, the electricity was flowing, the energy was flowing. And it happened about the end of 19th century that you can able to buy light bulbs from the shop. 100 years ago, the same thing happened to the information, that we were able to transport information from one place to another, first via telegraphs, and then phones and radios and so on, and the internet and so on. In this century, the same will be done for matter, for objects, for stuff. It's gonna be warehouses, like robots moving stuff. It's gonna be autonomous cars and trucks, and it's gonna be Starship robots, or not Starship, hopefully Starship robots. It's gonna be robots and flying drones, and that's what we are there, part of it. And if you think about what was the impact to the society for the first one, for the second, it's not gonna be the less for the third one. The society will be transformed so completely that it's impossible to even think about it. Like if the internet was invented, we didn't know that the Google, Facebook and stuff will come out of it. It was impossible to predict. The same stuff will probably be here, but we don't know what it will bring us. In Starship, before we go to the main topic, I want to mention one thing, crucial thing, that it's not only about these robots, it's a lot more. It's about where they live, because if there are no humans, they need to go somewhere. It's about their battery swapping and energy. Actually, it's about apps for kitchens, apps for people rescuing and repairing the robots, systems for humans to help the robots, apps for consumer to do it. So the whole IT infrastructure there is huge. It's not just robots. And being the first to do a self-driving robot, it's not trivial either, but it is a lot more. It's the full system there. And it is now a reality. It's not anymore. We are not doing technology development anymore. We are scaling the business. For example, last month, we did more than 10,000 deliveries that we got paid. And now we are aiming to be profitable, operationally profitable in some areas. and then scaling the business. That's it. The Zen of data science, or ecosystem of doing things with data, it's different. In school, when or in university, when we study about computer science, or then it's about planning, maybe these drawing some boxes of, I don't know what they mean, like some data tables or it's about kind of flow of doing the planning and executing and testing and QA and so on. That's not how innovation works. There is no pre-planned steps that you execute in row and you know how much time there is. It's not at all like this. It is a chaotic place where people kind of interact and they solve problems. And for us, it sometimes feels that we are even lacking vocabulary for it. We are even lacking how to describe it, because we are trying to use these words that we studied from school or maybe from 200 years ago, and okay, maybe 100 years ago when they started producing cars or whatever. So we have been thinking and we started using some vocabulary, and it turns out that other people started using it. And then when I heard that people also outside of Starship are using it, in Veriff, for example, then I thought that, oh, it's quite cool. There may be something in it. And we didn't find similar vocabulary in Silicon Valley, like blogs or textbooks. And so we realized that actually we are in a front of innovation, where we are not just inventing new technologies and new services and having impact to the society, but while doing it, we are also inventing new ways about thinking about the problem. We published this manifesto, Data is the Specification, a manifesto for iteratively solving complex problems. It was published by me, Taivo Rao, and Ahti. Ahti is the co-founder of Starship and CTO of Starship. Also did some other things like Skype and Kasa and stuff. You can read it here. Data is spec.github.io. I'm gonna quickly go over the 3 main points, and then we can discuss it, because it is not kind of clear. It's not that it's kind of well defined that I'm using some philosophers' ideas that I can cite on. Like, we are just inventing the term as it goes. It's not something that we can define well and kind of reference some textbooks. It's like a work in progress. The principles are, instead of coming up with a good general solution, it is better to focus on solving a specific cases of the problem. That's one of the interesting things why we thought that this thing is not the way how Silicon Valley is doing stuff, is that Silicon Valley is quite often taking on rather like kind of, how do you say, monumental projects like CPUs, rockets, cars, and so on. There is a lot of planning ahead, and you cannot experiment. You cannot kind of, okay, you can, SpaceX maybe blew up about 6 rockets, but you cannot blow up like 1,000. It just doesn't make sense. And you cannot, I mean, Tesla has maybe killed 2 people or something, but you cannot kill people in thousands. There are limits to your experimentation, what you can do. But for many cases, you can do it. If you're iterating your organizing parties or hiring people, or if you're working with so small robots like our robots that it doesn't matter if you're getting it wrong, or if you're doing just software like Veriff, then you can iterate the complex problem against the data. So focusing on specific cases, not huge design, and this principle, it also is quite strange that people didn't believe that this is possible like 10 years ago. I think it's a new understanding for human society that maybe even machine learning or deep learning was the reason why people started to believe it, that you can make a superhuman system by iterating with small steps against the data. Like deep learning is doing it. The way how we play Go or we understand the images or we generate sound, the model is iterating step by step against data. And we are getting into superhuman state in end. I think that's one reason why we can kind of assume that there is something there. You don't need to have a general huge design to build something great. Principle 2. Instead of trying to solve all the problematic cases right away, it's better to address a proportion of the easiest cases and repeat the process multiple times. That's very, very important. Like in Starship, we started measuring like how dangerous is the robot, how often the robot would be killed by a car, and we realized that maybe things are not that good. That we need to improve the safety of the robot about 1,000 times. It was about 3 years ago, and improving something 1,000 times is like I was head of computer vision and perception at that time, and I was kind of out of my face, like completely sad. Of course, I invented the measurements to even know about the problem, but I was still sad. That didn't help that I understood that we have a problem. And then, like it was Ahti who said it that like don't worry, like take the list of cases, take all the problems that happened in a day or in a week, and take most important of them. Like don't think about the rest, and only solve half of the easiest cases. And solving easiest cases is rather easy. Usually they are kind of random thing that happened that you can actually fix, a software bug, some kind of system. Of course, you can put new sensors or you can just avoid some crossings, or you can do a lot of things. But always solving the easiest cases is doable. But if you solved half of the cases, then the robot got 2 times better. Now you have to repeat the process 10 times, and the robot is 1,000 times better. And that's what we did. We solved half of the easiest cases 10 times. While doing it, it was motivating. We were able to solve it. We got better, smarter, and some of the problems somehow disappeared as well. If you would have started to kind of have a plan of like solving all the problematic cases, some of them might have been impossible. But somehow the business model drifted into different places and some of these things disappeared and so on. So it somehow worked out, and it is a wise idea, I think. Of course, we wrote it, so we believe in it. Principle 3. Instead of writing a good specification of a solution, it is better to curate a collection of good problem cases. Again, people tend to write very good specifications, writing down what needs to be done. And the worst thing is that sometimes they only give the specification to a programmer. But if you are giving it in Starship especially, like all the programmers are just so good, if you're just giving the specification, you're losing everything there is in their mind that how they can be creative. It doesn't make sense that the manager knows the solution better than these high-tech people. If you're not doing this middle aggregation step, but you're instead giving all the cases to the low-level implementers or programmers, basically problem solvers, then you don't lose vital information. You're not making wrong conclusions in this aggregation step. You're empowering them, you're motivating them, and actually they will have a better solution than you as a manager to these problems. Whatever, it might not be a manager, it might be a group of people who are actually technical and well, but still, while solving these cases, if someone has written up the solution, you're losing up the complexity of real world. And this curate the collection, that's important as well, that became or that is still our specification. We are not just saying that, oh, you 10 programmers or this team, like make it a bit better and you make it better. We are all analyzing all the problematic cases, and then we are grouping similar ones together. For example, all car cases that happened at nighttime where, I don't know, the car was very fast. And then we are giving these to a group of people and then they are trying to solve it. So we are kind of thinking about like possible groups of problems that can be solved. I'm now talking about the robot, but it can be anything. At the moment, I'm head of data team, and one of our tasks is to solve the estimated time of arrival, like ETA number that is shown to the client. We're doing the same thing. Every time we have shown a bad ETA, we collect these cases. Like every week, we are going over about 50 worst of these. And then we are checking how can we solve it. Sometimes it was about, like at the moment, once it was because the system didn't know that there will be a shortage of human operators who will help the robots. So about like third of the cases were related to the shortage of human robots. We are taking these, giving them to some teams, to please, let's solve this kind of issue. And then we are solving it. So like it works in different teams, it works in different levels, and I have never written a specification. Seems like a bad idea. One thing that really well fits into this thing, as you can see, this thing is like a general problem-solving framework. It's like a, I don't know, like a brainstorming framework or like Scrum is, or it's very high level. It can work for many things. For example, 10 people have left your company. Like, let's try to do a company better such that they wouldn't have left. And now, instead of just thinking of the solution that let's have regular parties, and then someone starts organizing some random parties, you're actually giving these interviews and test cases with these 10 people to the people who are organizing the parties so that they will try to fit this party and the main reason for these people. So you can kind of do it even if it's just an HR, even if it's not the programming, not the program, like a technical problem. But for technical problems, there is a very, very like special case there why it's a good idea what to do. It frames a problem as a machine learning problem. If you have test cases and you need to solve them, it's like, you know, machine learning. You have data and you kind of need some software that solves the data. And that's very much part of it. And that's another kind of framework or vocabulary that we are using a lot, or we are all thinking about it, is a machine learning continuum that this terminology, software 1.0 and software 2.0, was, I think, coined by Karpati, the deep learning guy, and that there is an algorithm and there is a proper machine learning that replaces algorithms, that you can just have this kind of matrices that is a neural network. But actually, it's very gradual stuff that if you have an algorithm, the next step is that you might have test cases and you might have a scoring against this. So if you have two algorithms, you know which of these is better. But if you can already do it, then why not to do some automatic parameter optimization in these algorithms? Then you can automatically know, like iterate like thousands of these similar programs and see which one is better. But then like kind of that's very close to machine learning, that you're actually optimizing against the data. And then there is a proper end-to-end stuff that you're doing a proper deep learning. And that's another misconception, that people tend to think that if you're building autonomous robots, that you're quite often somewhere in here. Actually, 99.9% of the code is somewhere in here. And the main reason for this is that it's just more simple. Humans are smarter. They can write code that generalizes well out of the data, but that doesn't mean that we don't use the same vocabulary. We still have test cases. We still have false positives, true positives, and so on. And I can sum it up with a need of data, that how much data you need in order to have in any of these steps. If it's just an algorithm, then you don't need any data. Test cases, automated scoring, comparing two functions, which is better. 10 cases are almost enough. You're getting a statistically significant result if it's like 3 cases is different. Parameter optimization, depending on how many parameters are you optimizing. If it's one parameter, then 100 cases enough. It grows a bit exponentially, but still. Machine learning, usually if you're already doing some, for a lot of features, you're fitting some hyperplane. It's difficult if you have less than 1,000 cases. Depending on number of parameters, maybe tens of hundreds of thousands is good. doing end-to-end proper deep learning with these neural networks, it's difficult if you have less than 1 million. Probably you need tens of millions or hundreds if you're building self-driving robots. And that's why we have a whole, like, I don't know, 20 people full-time in Africa annotating these for last 3 years just to have this one end-to-end model. You don't want to go there. You have to write some text for them to teach them how to annotate, and basically, you want to be somewhere here actually. But it doesn't mean that you don't think like a machine learning engineer. You still think like a machine learning engineer. It is an interactive session. There are a lot of questions there. Where do these things apply? How do you use them? Whether they will apply in your situation? Whether this makes sense at all, because we already have data-driven decision making, and we have unit tests, and we have machine learning. Why do you invent a new term at all? So please, the critique is on you. No, on me, by you. And yeah.
Okay, we have one question over here.
Thank you.
Thanks, Christian. So you showed this list of software 1.0 and software 2.0, and kind of my first reaction was that you were somehow that kind of when I saw this slide, for me it implied that software 2.0 is better than software 1.0. But I think you kind of hinted that you don't really always want to be there. So you always never want. So it's so maybe kind of ranking them in this way is kind of maybe kind of counterproductive in a sense that if you really have an accurate algorithm, you don't want to replace it with deep learning if the algorithm is accurate.
Yes, usually the accuracy goes up here, but also the interpretability goes down, and also the data need goes up. Both of these things are harmful, but accuracy goes this thing, you will never write so good code. It is powerful for complex problems where you have data and so on. So I think the accuracy goes up, but there are a lot of losses as well, data needs and interpretability. And sometimes the speed as well. Sometimes you can write more efficient code. But I wouldn't say that it is ranking. I didn't invent the term software owner 2.0, so it's not my fault. If I could kind of invent a new term, then I would maybe, but I'm not in a position to argue with Karpati.
Thanks.
Okay, everyone, someone else?
But thank you, makes sense.
I also had one question. What about non-functional requirements? Are they somehow outside of this framework, or especially with robots, you count every last bit, so
is it working?
Yeah.
What about non-functional?
For example, how much memory these will take, or what's the computational resources for it, and so on.
Mm-hmm. Yeah, surprisingly, when we are building stuff, we don't think about it too much. First of all, you can always kind of take 10 more servers from Amazon and the problem solved, especially if you're like creating innovation. If you need to optimize later, then yes. And in a similar strange way, we don't have some computational budgets in the robot for different teams. Like everyone uses as much as kind of powerful way possible, pushes each other, and then if problem is there that because of the computational constraints, or because we didn't have enough compute, or we started using the swap memory files from the hard drive, then we will start solving it. If the accident was made because of that, but not before. We don't write this into the specification. It kind of, maybe then it kind of implies that most of the programmers should be senior programmers who are extremely good, that you know it implicitly somehow that you're trying to be decent with the computational resource and with other requirements. And the same stuff with like ETA calculation. We have a lot of kind of microservices that offers a lot of things that are surprisingly complex. You need to estimate battery levels, whether like driving operator load, blah, blah, like huge system there. We just write it, and then sometimes we see that, some numbers are in a final kind of action zeros. and then we investigate, oh, one function took too much time to compute, then we will solve it. But before that, I mean, why think ahead if you even don't know whether you will use the function again in a month?
Yeah. Thank you.
Thank you. Thank you, Christian. I had one question when you described that if you have problems in the data, you give the curated data to the team. What's the difference if the team makes the solution versus the management makes the solution? Where does the positive side comes from? Well, let's say the management is super smart as well.
Yeah. I think you mean this one.
Yes.
That's not about the curation, is not the main thing there. It's about specification. Don't write down the specification that, oh, we need a new sensor that sees about 60 meters. Also, if there is a moderate rain, also when it's a bit dark. Like, don't start writing it down as a specification. When we are choosing a new sensor, we are listing the cases that we are unable to solve. We are taking a couple of sensor options, and we are seeing how many of them it would have been solved, and we are taking the sensor that solved most of them. So we are not aiming to do this middle level of aggregation of writing it down, what are we trying to aim. We are taking the test cases there.
But in the end, it's still a specification?
Yes. And the title of the talk was Data is the specification.
Yeah. But will you write it down, or what will go forward? Well, let's say the team looks at the...
what will go forward for us, it depends on the situation. If we are improving the robot, then usually it is a robot name, start and end time step in Unix code. So you know the situation when it happened, and then every developer can download all the data. If it is related to estimated time of arrival, then it is the order number, and this goes forward. I'm only taking 2 examples to simplify here stuff. We are doing more in Starship than robots and ETA. It's just out of these thousands of problems, I'm taking 2 in here to simplify.
But, well, I mean, what's this? Well, the team gets the data specification. They, in the end, through the data, define what is needed to solve the cases. Then they write the specification, but
no,
they need to make the changes.
They don't write the specification.
Okay, so they just make this change.
Then they do a code change, commit, push, master, deploy it.
Okay.
It's not a joke, we don't have branches.
Thank you, Christian, for the talk. The principles were quite straightforward, so it's hard to criticize them. I would also go for the last slide in the kind of software and software 2.0. My question is, why in software 2.0 we are considering end-to-end deep learning rather than kind of end-to-end optimization in general, as like deep learning is one framework within the range of optimization. But if we're talking about like general problems in software, then we could use any of the optimization algorithms.
Sure. If without kind of doing any feature engineering and giving the raw crazy data in and wanting like kind of a superhuman solution, then unfortunately there are almost no successful algorithms at the moment. So it was just a specific case to illustrate the point. Of course, even Karpati, when he defined the term, even in his blog post, he says that actually it is any kind of superhuman solution against the problem. Yes, it doesn't have to be deep learning, but again, it tends to be.
No, I mean, just like 5 years ago, it was, okay, not 5
years ago. It was
deep
learning already.
Yeah, then it was already deep learning, but 10 years ago, it was like support vector machines.
Sure, but then software 2.0 term was not invented because it didn't make sense.
Okay, sure.
You cannot give a raw, noisy data into support vector machine. Cannot handle it. You are not producing something that is better than a human code, but you can do it for deep learning. I mean, it is just a terminology. I already agree with you. This is a specification to make it easier for you to read. But I could say like a superhuman optimizer. A valid point.
Okay. Thanks for presentation. A bit maybe out of scope, but anyway, based on this last slide, the new goal is a data. The data is a new goal, so you're collecting. The question is that are you in Starship actually using the data what you collect also for other purposes or making other ideas or whatever? I mean, you collect data also what people deliver, when, how they live, exactly. So all this collection, so this is all the data, yes. Just, I might be wrong, but you please correct me, but isn't company Twilio, which also established by ex-Skype employees, but the investor wanted, they heard the headquarters must be in US. They are buying API for applications, for telecom API for applications anyway, yeah. So, did you get the bit long question correct?
The last bit drifted off a bit, but in the beginning, I think the question was, are we using the data in other ways as well than... So, I can answer maybe in my way, like politicians. It would be lovely if we could sell some of the data. Then we could earn more money. But so far it hasn't been too successful. At the moment we are not selling any of it. But there are a lot of talks that we can sell, for example, payment quality information to local governments or anything like this. So in that purest sense, what is this, like sometimes chief data officers in big corporations, they're sometimes aiming to also have this in the company, that you will be able to use your data outside of your company. Then inside of the company, it is of course the case that absolutely every decision, everything goes via data. And that's part of the premise for modern companies. For example, our CEO at the moment is the ex board member or ex management person in Airbnb. And when he left Airbnb, there was a data science department, and there were 300 data scientists just for Airbnb, and it's even more for Uber. And people believe that it's the only way to create success or great companies, like powerful companies, to have these huge data science teams. And the reason is that the company makes tens of thousands of decisions all the time by everyone, by every middle-level manager, by every manager, even clients and so on. Everyone makes constant decisions. That's what you do at your job. And if you're making these decisions, if you can do them based on data, they will be a bit more rational, a bit better. And if your tens of thousands of decisions every week or month are a bit better, only then your company can be the greatest. So data science and data has like a huge role inside of a company for every modern company.
One more, coming to this principle tree. I really like the principle tree about this, the curation, curating specific cases.
I think it's well spotted. I think it's one of the most crucial aspects as well in this new form of management, let's say.
Yeah, and actually it seems to me that kind of the main management challenge is curating the right things. So can you elaborate a bit, and like curating them well? So can you elaborate a bit, how do you do the curation? How do you decide which metrics are worth to be kind of to curate cases on? Mm-hmm. So because that kind of defines what kind of problems you will be solving.
Yeah, of course the same problem applies for writing specifications. What type of problem do you solve with the specification, and to who do you send it, and so on. So it's not, even if I'm unable to answer, it's not going to be critique against this thing. Just to be sure. Yes, it is a
I wasn't trying to criticize. I was just trying to understand your processes.
It is, of course, kind of a complex issue in a sense that, for example, we might not be able to cross some roads because it's too complex. We would be making too many decisions there, or too many mistakes there. There are so many ways who can solve this problem. For example, software engineers can write better code for us to detect cars better. But we could also try to avoid this crossing and cross another crossing. Or we could try to avoid this kind of city at all. Or avoid all the crossings and go only to university campuses. Or we could still drive there, but buy a new sensor. So the question is always what to do. And I guess that's big part of the kind of constant decision making and being aware of what's going on. But the same decision needs to be solved anyway, even if I'm writing a specification. And it is, I guess, its most exciting part. Like, how do we make our vision reality that the stuff moves for free? And you can use any means possible. And that's, I guess, is part of this engineering innovation that you need to do it. But I don't have a clear answer, but being mindful for that maybe usually we have meetings where there are a lot of different people and we are going over these cases, and then all the opinions are there, and basically whoever can solve them cheapest gets the data to himself and will solve it. And of course, if things are very high level, choosing business model or whatever, then the less and less the data is important, and you need to have creativity and vision and some other things. But still, you get your intuition from all these cases.
You still need creativity to define like the metrics of where you're failing.
Yes.
Which is, I think, also kind of to get the cases in the first place. You need
Yes.
to know that you're failing.
Yes, but many times it's very easy. You lost a customer. Bad. Robot was killed. Bad. Like, I mean, you got the 0 NPS score or 0 score of would you recommend it to your friend, or less than 6, you got this, would you recommend it to your friend? You can analyze all these things. You would like to make the company more profitable. You see where are you losing your money, biggest chunk goes here, let's solve that one. I mean, it's not rocket science actually to understand the biggest problems of a company. Solving them is harder actually.
I have kind of similar question. Like, if you are a startup claiming to have an AI or aiming to have an AI, when you in realistic world you can really implement it, and what to do before that?
I think all these ways of thinking in terms of data, machine learning continuum, Taivo has a good vocabulary, unit of automation. Even if people are doing some work, doesn't matter. If you know that in principle with 1,000 engineers, it is possible to automate it, that's fine. You will automate it when you have 10,000 employees doing it. You don't have to automate it now. You have to just think and frame and do all your business build up in such a way that it is impossible. You can automate it in the future, and that's enough. That's enough to get clients, money, everything, and you can start doing it. So I wouldn't critique too much companies who haven't done it yet, because if it's clear that they can do it, that's enough. That's the stuff that startups are doing. They don't say that they have a lot of clients, a lot of good products. They say that they will have a lot of clients and they will have a good product, but they have a plan that makes sense. And one part of the plan is being data-driven, making your company so that you can start automating everything end-to-end, and you will only have software. But if you don't have it in the beginning, it's fine. Starship robots didn't even drive for the first half a year because there was no robots. We were just building them. Like, of course there is no AI either. And when I joined Starship, I was employee number 20. It was 3.5 years ago. We had 0 machine learning there. All the robots were driving. But it's still AI first company, because without automation, without AI, it would be impossible to scale and be profitable. So I wouldn't kind of be too old school with related to whether AI is there at the moment or not. It matters how you basically think big, how you organize your stuff so that it will be there in the future, meaning that you can automate the humans out.
Okay, let's take our last question now.
Oh, cool. I get to be the last one. I have one comment and then one curiosity. As far as comment goes, the principles that you outlined, my background is way back when Air Force. So when you look how Air Force is doing its operational planning, for past 10, 15 years, it has been surprisingly similar, being not a solution or task-based, but effects and objectives-based. So the thing that you say is a case, they say it's an effect or objective, and you find the approach similar. Anyways, the curiosity is then how do you know when you have solved a specific case of a problem?
Mm-hmm. Good question. I guess that was part of this related to the previous comment. If you don't have any AI yet, whether it is an AI company, usually if you are talking about AI company, then the problems are defined by data flowing in and the decision coming out. And now, if the decision came out wrong, the data still came in, and you can record the data. And now, if you change the code or systems, then you can test it offline, whether now it is solved or not. So basically, in most cases, like if we didn't detect this one car, then now we are changing the code. We can replay the situation and whether we are now seeing the car or not. Of course, it doesn't work too well with buying a new sensor, and it doesn't work too well sometimes for interactive decisions. But for these two examples, seeing cars and ETA, you have all the data. So if you are doing your software changes later, you can replay this historical situation.
However, if you have minuscule change in data, so you have slightly different situation, then you need to test these cases also, because otherwise you just fix yourself on one specific point in your solution space.
Mm-hmm. I guess that's why this slide comes to be useful. That's why we do use mostly writing our own algorithm and testing these things, yes. Because then we don't need that many testing cases. Then the human mind is responsible for making a generalization so that it would work in all the cities, in all the weathers and so on. So the human mind must be there. Of course, if you're blindly optimizing this one case, that would be a very stupid thing to do. But of course, the whole company wants to fulfill the mission. And then it's not, the aim is not to solve this case. The aim is solve a general case and then see whether this general solution solved that one case as well. And that's how you operate. But you need to, of course, be honest with yourself, because you can. It doesn't make sense, because even if you solve this one case, the next day you will have the similar problem in a similar ways. Then it doesn't go away. Then it comes again and again until you solve it in a general case when it kind of works for new places as well. And like Starship kind of drives on new streets basically every day, because we're expanding. More and more robots are coming out and they're going to new places with new customers and so on. You cannot solve it for that one case. It must be general, otherwise these same cases will be coming from these new places, and you are not advancing your main company KPIs, which would be like autonomy, safety, profitability, and so on. These will not go up otherwise. So yes, and that's why also you cannot do this software 2.0. If you only have 10 cases, then this will produce some completely meaningless crap, and it doesn't generalize even to 11th case. That's why you need more data, otherwise it will not generalize. But humans are extremely good at it. I can see a couple of cases, write some code, and it will work for tens of thousands more. Deep learning cannot do it.
Thank you very much, Christian. Our next speaker is Taivo Pungas. He is automation lead at Veriff. He got his master's in ETH Zurich. And if you don't know about it, that's the place where also Albert Einstein and John von Neumann went. So we have hopes, big hopes here for Taivo. He's also contributed a lot to data science community, as his datasci.e web page and Facebook post was one of the earliest materials available here. And now he writes AI-related blog, taivo.ai, which has some good articles, and hopefully soon also this topic would be fair. So, are you ready?
Thanks.
Okay, let's hear it from Taivo.
Thanks for the long introduction. Nicely fit for the technical setup. To what Christian said about hiring each other's brothers, it's true, but he did it first, so that's basically his fault. I want to do a quick survey of who are the people here. So raise your hand if you are working daily in the following role, and you can overlap different roles. You can do so raise your hand several times. Data scientist. Okay, software engineer. Product owner, data analyst. Okay, I think we covered a total of like 90% of the people. I don't know who else is here who hasn't raised their hand. What do you do? What do you do? Apparently. Okay, nice. On my last slide, we have the careers page link. So. All right, so I will get to what I mean by the title of the talk later. But before I go into the topic, the experimental here, it means that this is a concept that I sort of extracted from the way we work. It's not super advanced or anything. I think it describes how we work at Verif in the automation team, but I don't know how well generalizable it is. So this is something we can figure out tonight in this discussion. Does it work for you guys as well? Before we go into the tulips, let me explain what Verif does. Our product is basically online identity verification by showing your document. So the way it works is, you want to rent a car, and the car rental place wants to verify that you're actually, you have a driver's license and are over the age of 18. So what they do, they send you to our flow, to the Verif app or website. You choose what kind of document you have, take a picture of yourself, of your document, both sides, and a picture with yourself and document, and then you're basically finished. And then in the background, Verif does all the work of looking at these images, figuring out if you are who you claim you are, detecting fraud, and giving out the final answer to the car rental place of, are you actually who you claim you are? And the larger idea behind that, or what we're aiming for, is that if you think about the internet as a network, and not in the sense, in the technical sense of like servers and routers and packets running over cables, in a sense of connecting people to each other, connecting companies to people, then just having this internet connection doesn't really automatically make you want to use that connection, right? Because you can't trust the other people, or you can't trust who is on the other side of that line. And what Verif is aiming at is enabling this trust online. So layering over this technical communication infrastructure, laying over a trust network, basically. So how we think about automation at Verif is that when the user finishes their verification, then all of the data that the user took and all the data we have goes into the automated system. The automated system can give an automatic decline, automatic approve, or you can say that, I'm not quite sure, and let's ask a human. And this is sort of makes it easier to do this automation because you don't need to do 100% automation from day one. You can start with only humans. And then as you sort of work your way through the easiest cases or easiest things to automate, you can gradually increase your automation level. And the automated system here, this is most generally what I am responsible for, or my team is responsible for. And this is something I call, like specifically in these slides, I call an algorithmic product. So my slides or my presentation is about how do you use or how do you sort of adapt the build, measure, learn loop for building algorithmic products. Who knows this loop? Who has previously seen it somewhere? Okay, it's from Lean Startup, the community handbook, and what it basically means, it's like, the sort of high-level version is pretty trivial, I would say, is that the way to build a good product is to build something, then measure how it's doing, learn from it, and then repeat many, many times. And this, by doing this, you can sort of iteratively get better. And I think you can probably already see how this ties in with what Christian spoke about. So there's this loop. Now, my title said I have 2 loops. The first loop is the algorithm development loop. So this is, again, a build, measure, learn loop. What we build in this case is algorithms. For example, let's say we want to build an algorithm for finding out where a document is in an image. We build the algorithm, we run the algorithm, we measure it against some data set. Just some validation data set, doesn't have to be trained on anything. Could be a very simple algorithm that, 2 lines of OpenCV help you find the document, and then you can measure it against the data set. The output from that is basically metrics. You have defined yourself like pixel-wise error or per image error, or however you define your loss function. You measure that, learn from it, get ideas, and that feeds back into the algorithm development part. Does this make sense? Cool. There's another sort of internal loop here where what you learn from the failures goes into the dataset as data points. So it may be that your dataset is basically wrongly annotated. In some cases, in the annotation, someone has drawn a box of the document simply in the wrong place. Or it could be that you figure out in this place that you don't have enough data for training your model here. You don't have enough data of passports, but you have enough for identity cards. Whatever, in any case, from this point, you can also feed directly data into the dataset there. And this is the algorithm development loop. It's very simple. And I think if you've been building a data science related product, you're probably familiar with that. The sort of tooling or things you use here at each step is algorithm frameworks, obviously in the algorithm step. In our case, it could be OpenCV because we work a lot with images and videos. Could be TensorFlow if you're building a neural network. In the measuring part, it's actually a bit more complicated, I would say, because sort of the task definition is given by the data. The data is the spec, which means that the data set that you put together very much defines the problem. So it's not just putting together the data set. It's the putting together the data set part is sort of where you define what needs to be done. And obviously, there's a lot of tooling that and process that goes into there as well. If you want to annotate large amounts of data, in the case of finding documents and images, Christian's Africa example is a very common one. You might want to outsource your annotation, send 10,000 images there, ask them to draw boxes according to some specification, and it seems kind of straightforward. Like, how hard can it be to draw boxes, right? But then your expectations hit the reality, and for example, you see that, okay, just a simple rectangular box doesn't suffice. because people can also rotate their document, accidentally or on purpose. And even a polygon, like a 4-sided polygon, does not suffice because people have passwords. They have 2 sheets, and they sort of fold into a shape that is not well described by a quadrilateral. Or, you know, could be that because of the camera optics, it's not even straight lines anymore on the document, even though the document physically has straight lines. Just the optics might bend it to have like basically round edges or slightly round edges. And all of this needs to be sort of somehow handled in the annotation spec. Also, if you want to do this on a large scale, you need tooling to do this. So typically, this whole loop is handled by a single data scientist. But when you hit a point where you want to sort of tease out problems or errors that happen once in 1,000 cases, you really need to start running your algorithms on tens or hundreds of thousands of data points. And for this, you know, just running stuff on your laptop or on your single AWS machine doesn't suffice. And down here, this is kind of, partly this is just classical data analysis, but partly this is also the tooling you need there is basically transparency or visibility into what your algorithm is doing. You know, you somehow need a debugger or debug view of what was happening inside the black box that you measured here, or measured with like the high-level numerical metric. Cool. Does this make sense? I think I see less notes this time, so I'm losing people every time. There's like 2 people left. When I hit 0, I will finish cut off the presentation. So the kinds of people or the roles basically that work within each step at Veriff is data scientists, or you know, you can call them also software engineers or computer vision engineers or whatever the title, but generally they're people who build algorithms. There are people who annotate data, maybe in-house, maybe outsourced. There are people who define what the data set is, and like this is often a product question, or if it's sort of an internal-facing product or a back-end system, then it's role-wise it may be someone else, but basically this is like a where you define the product somehow. To build these large-scale tools, data scientists usually don't have this software engineering capability, or to put it in another way, the code that data scientists write, if you're a software engineer and you have seen it, you know what I mean. And this is okay, because these people are not selected or hired for their ability to write clean code and you know, deploy it to thousands of servers. This is I mean, you could find people who are good at both this part and this part here, but I mean, do you really want to pay like 20,000 euros a month to combine 2 people into one? So you kind of need to figure out how to use everyone's strengths and not require everyone to be like a super generalist. And here again, it could be the same data scientist, and usually it makes sense if it's the same person who built the algorithm is kind of the person learning from the mistakes there. That's fairly obvious. Who is still with me? Okay, several people. I can still continue. Cool. Now the second loop. The second loop is closer, I think, to the classical product development loop. But let me explain. So basically, you build products. This could be on top of the document, you know, the document localization example I spoke about before. What's a product you could build on top of that? You know, other than the sort of the obvious Veriff product, maybe you want to sell a product that tells you, let's say, document classification. You have your own sort of KYC department, but you want to route requests based on which country the document is from. So you will benefit from document classification. The product here in this case could be like a good document classification model. I mean, this is a kind of a contrived example, but basically you build some sort of product. And the product is, I think it's aptly called the production. You measure it in production, how well does it work, usage metrics, performance metrics in terms of like runtime, could be performance metrics in terms of how well the model is performing. And generally here you measure like the business value basically, not the algorithm performance. You get either live or it could be historical performance data, learn from your failures, fix bugs, get ideas to improve things, and then sort of run this loop. Does this make sense? Good. This is the product development loop. And the sort of, I think you're more familiar with the tooling generally that goes into this, but to build a product, like generally, how do you build a website or a service, or it really differs a lot between companies or what sort of product you're offering. You could use some queuing system and compute scheduling system. If you're a very front-end oriented company, you would have React there or whatever. This is not really important. You need to, when you want to measure what's going on in production, you need to have some sort of instrumentation, monitoring, logging, and here, to analyze what's going on, you have some sort of BI tool, business intelligence tool, dashboards, analyze the data that's coming in. Could be also real-time, something like Grafana or New Relic. And the sorts of people or the roles that drive this loop, generally this is driven by a product owner, or the product owner is sort of responsible for making sure that what comes out of here, that this loop runs well, and what comes out of here is actually the thing that needs to be built. Software engineers build the sort of the technical side of the products. There's obviously designers and the UX researchers as well, classically, but I focus on the technical part. Software engineers here as well, data scientists, and now their focus here is not on algorithms, it's more about data analytics. But people also call this role data scientists today. So how do we put the two loops together? This is the first loop. And when you have run this loop many times, you figure out that your algorithm is good enough to put to production. You feed it into the other loop, put it into production, measure it. Could do this loop several times, but basically, once it's in production and producing data or showing some sorts of results, good or bad, you can take what you learn here and put this back into the dataset. So let me give you an example. We built, we have a system for extracting data from documents, and this data extraction part. There are several steps. You need to figure out what the characters are in the image, OCR. You need to figure out which field they belong into. Is it this like the first name or the date of birth or whatever? You need to sort of do some post-processing on top of that, because dates have different formats. Document numbers are not always represented nicely in like a single string. And what happened recently was that some driver's licenses in the US, sort of the document number can be kind of embedded into another field. So it could be that your personal ID code, or vice versa actually, your personal ID code forms part of the document number, and to get the personal ID code, isikukood in Estonia, you have to extract the document number and then sort of cut it into pieces and then figure out where the personal ID code is. And this, we built a system to do that, to extract the data from documents, put it into production. We knew roughly how well it measured against our sort of offline data sets. Put it into production, and in sort of quality assurance or reviews, which we do, we sort of, for all the automation, we look into, in this step, we have humans looking into what was happening or what was going wrong. And we figured out that somehow the cutting was not correct. But instead of sort of, like Christian said, instead of specifying, this is what is going wrong. I did like a deep dive on the code. This is where this is the functionality that is missing or that is wrong. You give the people doing the review gave us here are 5 links or 5 IDs of the verifications where this happened. This was the actual this was the sort of the output that the system produced. This is the output that the system should have produced. And this is the specification for fixing the bug. So this is the bug report, basically. And this is very easy to fix, because if you have this testing system, even if you don't have thousands of test cases, you can just run those 5 cases through here, do this loop, fix the, make changes in the code until you know that you have fixed these 5 cases. Does that make sense? Good. And let me give you an example of different flavors of going through this these 2 loops. So this is the same problem I was talking about, finding out where the document is in the image. We call it document localization. You could start by creating a large data set, 1,000, maybe 10,000, 1 million, however many images, which you annotate with these boxes, and then train a neural network on top of that. This could be sort of your first approach. But the first step to train a neural network, you need a large data set. So you can start with putting together a large data set. And the way it works is then you sort of start in this step. You define your data set, you annotate a bunch of data. I guess you kind of skip this step because there's nothing to learn from, then build the algorithm, run this loop as long as necessary, and then go into this loop and sort of integrate it into production. How do you get the data if you don't have a product? Right. So how do you get the data if you don't have customers or you don't have a running product yet? I will get to that point in a second. It's right. But I mean, oftentimes a data science or automation team is hired afterwards, like when you have a product running. But in principle, you could also sort of, so Christian said that it's better to start with running product, basically, especially as a startup. But you could, in principle, think about a product that you can put together as, from scratch, basically. You create the data set and then productize the model on top of that. One example is that from the Zurich computer vision group, there was recently a paper where they took basically like a rig. They put a DSLR, a professional camera, and a smartphone next to each other very close. And then they took thousands of images with both exactly at the same time. And then they sort of learned the mapping from the bad smartphone image, or relatively good, but still worse than the professional one, to the professional looking one. And it worked surprisingly well. So you can imagine that after building this good model, you could easily create an app that, beautify your pictures for Instagram or whatever, or improve your shitty photography skills just by using our app. Could feasibly do this. I don't think this is the best approach anyway, but that is often kind of the, you have to bootstrap it somehow, right? And this is one way to do it. You can also do something like, this is my problem, and let me just write something that takes this image, finds it in this image, and it's 2 lines of code. It's literally 2 lines of code. And in that case, you basically start with the algorithm. You can start with the algorithm and just put it to your production. Then run it, collect data, come back with data set, and then keep iterating on the algorithm. And this is kind of how you solve it. You start with something that is based on almost zero data points, just something that you think would work at least a little bit. And the third kind of approach is you can just ask humans, build a product in such a way that this loop is never entered until you're basically ready. So you do everything manually at first. You buy professional mouses for people to do everything manually. And once you think you have enough data, you have a functioning product, then it makes sense to make the investment of automating this product. Cool. Does this make sense what I spoke about so far? Yeah. Cool. I would like some interactivity here. I think we don't have a typical Estonian audience because I heard some questions before. What do you think the hardest part of this whole loop is? And the next slide wasn't actually a hint. It was a separate topic. Say again? I like general AI. I mean, that doesn't usually. The last time it came to my table was like 2 months ago. So third one, so learning from failures, or sort of measuring and fourth one. Why was it? So okay, so kind of learning from the product side what is actually necessary. This is the hard part, and then like automating it later is relatively straightforward. Is that your point?
Yes, that's yes.
Okay. Who said something about data annotation or measuring against data set? Yeah. Can you elaborate? Can someone give you a mic? So what's the hard part, or like can you explain? I mean, I'm not sort of challenging you. I want to learn.
Yeah, I mean, like measuring against database. This is the hardest part, in my opinion, because sometimes you can figure out problems that you cannot solve and cannot build algorithm to solve it.
Mm-hmm. I guess then it's this step. You can't figure out an algorithm that solves this problem, or.
Just number 4 is measuring against dataset.
But can you expand on like what the difficult part there is? I didn't understand.
Sometimes you can the data that you have cannot provide you with accurate information about what type of algorithm you need to build.
Okay, so the dataset is basically like too small, yes, or too like not basically suitable for the algorithm you want to build. Okay. Wait.
Yes, I think if you, like you mentioned, this measure against dataset, and the dataset has to be chosen by someone. So someone makes the specification. Now this is based on what data? So if the algorithm loop is based on the data that you specify, so the specification is the data, then who specifies the data, and that's not specified by data. So I mean, it can be a problem.
So someone needs to have some idea of what the problem is that it needs to be solved, right?
Yeah,
and
exactly. And is that the right problem? You can solve a problem that it's not the problem actually.
Yeah, so I guess if you take the data spec example, what was an example that Christian said? There's a bug in the code that doesn't really, or I guess this is like a classical software bug. But let's say you forgot to account for the weirdness in the document number and the personal ID code that I mentioned. Then you can sort of, on a high level, say that this thing is wrong. But I think generally saying on a high level that it's wrong, sometimes it's even totally useless without the data. Like saying that we want to detect whether the image is blurry or not. Like, what is blurry image? Most images that you take with a smartphone are at least somewhat blurry. So like the canonical definition of the problem will be what the annotated data is. So that's a good point. Let me give you what I think about the difficult parts. But before that, let me sort of map this to functions in an organization, or what typically people mean. So people typically mean data science in this context would be like building the algorithms, measuring against the data set, learning from failures, but not the infrastructure part here. That's kind of like an afterthought that, I have my Python notebook, like the CSV is there, I'll just like pandas load and whatever. If you do it on a small scale, if you're alone in a company, that makes sense. But if there's like 10 of you, then that doesn't really scale anymore. You need to have shared data sets, shared infrastructure, do it on a large scale. So you need to have some other function covering that. We'll get to that in a bit. This generally, like we talked about before, this is classical software engineering or classical product development, basically, with one exception maybe. If the data scientist quality code that comes out of there is sort of not enough to put it into production, then you need to wrap it into a service or wrap it into somehow put it running on a server in your infrastructure. That's like the minimum amount of things you need to do, but usually that's not that hard because you take someone's existing code and wrap it into something. And this is also relatively well established. Like people have been doing this for 40 years, 50 years. There are established practices, processes for doing this well. The Agile Manifesto. So this is, I think, also not a very hard part. Data science also is not a very hard part, I would say, because this is recognized as a discipline. Like most of you are here because you have some inkling of what data science is or some interest in it, and this already means that like we have collectively figured out that data science is valuable. We should be talking about this, and there are two parts that are sort of almost completely unrecognized. Data annotation, like Ott said, this specifies a problem. This is super important. This is what sort of defines what happens when this algorithm is developed, when this loop is gone through, and what happens when the product is the algorithm is put inside the product. Data annotation, like can you name me companies that have anyone, like at least one person working on data annotation or responsible for it? Kaur. Yes, and Verif. There are two companies. But this is a very unrecognized area of building such products. And if you don't have a good data annotation team or a good data annotation function, then, I mean, you can build however good algorithms you want. If you sort of optimize it against the wrong data, then it's garbage in, garbage out. And another one is basically testing infrastructure, or this overlaps with data engineering or ML engineering a lot. But basically, how do you take these algorithms, or how do you that it would be even ideal, how would you give data scientists the ability to take their algorithms, push a button, and within 5 seconds get a response of how good was it? Because if you can enable this loop, if you can make this loop super easy, then you could have like one data scientist solving literally all of your problems, because the algorithm is usually not the hard part. So, I think you could build a successful data science organization by having 2 people here, 10 people here, and 2 people here, or 1. All right, so this is it from the formal part here. I want to hear your thoughts, but before we go to the Q&A, Verif is growing super fast. We are only limited by our supply, basically. We're not demand limited. This means that however quickly we can scale ourselves, our product, it's basically sort of kind of free money laying there, or free market laying there, and we can expand as quickly as we are able to improve ourselves. And for this reason, the automation team at Verif is expanding. And it's not just that we're hiring a software engineer and a data scientist. We're going to expand during this year by tens of people. In addition to the automation team, where we are hiring for data scientists, software engineers, data annotation people, all of them on from junior to senior level to team leads. Everyone is welcome to apply. We also have an analytics team, which sort of, for other product teams and also ours, handles this kind of learning part, which also is growing really fast. The growth is so fast that the job ads are not up yet. I haven't had time to write that, but I have time to tell you today. So this is my email if you want to talk about any of those things. By the way, we're also hiring product owners for automation. So if you're non-technical and you think you can contribute and want to be part of the journey, then let me know. Anyway, here's my email. We're growing fast. You know what to do. Thank you.
Thank you.
Excellent talk. I'm still kind of trying to understand what makes this kind of this annotation and infra hard, because it's like coming from, like my first guess would be that actually finding the product market fit is hard, finding a product that you should be developing, and then kind of this is kind of, in principle, it's just a technical solution. But is it what makes it hard? Is it that it's a technical solution that's underappreciated, so there's nobody knows how to do it well yet? Or
so when you said just a technical solution, it's the reason I laughed when Christian said just an HR problem, because like these problems are not easy. I think a big part is that it's an underappreciated problem. There's a big community working on data science problems. There's a long history of doing software engineering well. There's almost no one thinking about how do we do data annotation, like how does this function look like in an organization. There's very few people thinking, I mean, I haven't seen a product on the market that would help me make the testing system better or not build this in-house. So I think technically it's not like super complex. It's just that there's nothing out there and you need to custom build it every time. We did it at Starship, we did it at Verif, and there's nothing that to help you. So it's kind of like totally uncharted.
Okay, so maybe one direction to think about is kind of going for the academic sciences in biology and biocuration, where there's kind of huge efforts into developing standards of annotating data sets. Which, I mean, you can't lift them over one-to-one, but there might be useful things that kind of scientists have been doing for some time that's just kind of, that's not being used here yet.
Yeah, I guess it's not only about the format. Like you can annotate stuff in a very general and commonly agreed format, but there's still the question of like, what language did you write your algorithm in? How did you package it? How do you run it on the infrastructure that is available to you? How do you move the large amounts of data that are needed for the testing this algorithm? Because this, at scale, this also gets expensive. So I guess to get back to your question about original sort of, I guess, confusion, or you don't think this is so hard, I think this is somewhat specific to the stage we are at. So if you're just starting as a startup, then it's kind of important to figure out what your product is and that people want it. But as you hit scale or hit the scaling mode, you need to start figuring this out if your product is based, like heavily based on the algorithms that come out of here.
Thanks.
Hello, I'm Clavis from Indo-Baltic Chamber of Commerce and Industry. This is not so much technical question. A little commercial question, rather. As a Verif, it's a very promising say technology. You have Ashton Kutcher investing in you. And who, if you don't mind, would be your biggest customer or government? Do you have any government who is your customer? And if yes, why not a government of Estonia, who has launched e-residency? And all the people, especially from Asian countries, have to travel far off to collect their e-residency cards and give details why they cannot be verified through Verif technology. Thank you.
So about who our biggest client is, join our office. I will put you together with our CEO. He will tell you how we do everything and what the secrets are. And so that the actual answer is I can't discuss that, unfortunately. But to talk about e-residency, I would imagine that they have probably talked, like everyone knows, the community is small in Estonia. I would guess, I don't know, so this is just guesswork on my side. I would guess that the legal requirement for Estonia is to actually physically verify. I think it's in the law. When giving out, not the residence permit, actually, I think e-residency. I think so, but I don't know. So, if anyone from the e-residency team is here, then I have my business card ready.
With e-residency topic, you could maybe hire Christian's older brother. Also,
he recently was he left the managing director position, so I think he's free for challenges.
I have a thought, or well, I like to think. I read an article that described that it's not. Let's talk about machine teaching, and if you're a machine teacher, then the analogy of just software 1.0 or software 2.0, the difference is that for 1.0 we know how the code looks like. For 2.0, the code is the data. So I agree with you that the data what we choose is the code. And this is the decision or the algorithm that you actually make. So it's very interesting to how we look at it and how we choose the data. What's the processes of how to choose the data, how to define, because the algorithms, we can look like compilers. They just compile our stuff. We don't need to look at them much because they're quite good at already. They're not a problem. The problem is, how do we write the code? How do we debug the code?
Yeah, I think so just to expand on what you said, Andrei Karpati, when he was giving like the video bridge talk in Tartu like a year ago, what he said is that most of his time goes into writing specs for data annotation. Because that is the important part. The data is the important part. And neural networks are so good and so commonplace, the libraries are so standard that you can basically think of them as, there's a theorem called the universal approximation theorem, and that's almost what they are, at least for specific domains, like images, image classification. You know that the neural network can do it. Now it's a question of putting together the right data set to sort of teach the machine, like you said. But there's also a component of, the scale of software 1.0 to 2.0. I think the number increases as you increase the number of parameters that you tune from data, directly from data. Or maybe not directly, but by testing and or a human in the loop. Yes.
One point through that, we have always discussed today that the data is kind of image or something that the human, if he looks at it, he understands it. And I think that's the point why machine learning algorithms are really good with images, because we can annotate them. If a human looks at the image, he knows what's there. But if you're dealing with data that you look at, you have no idea what's going on, you can't classify it yourself, then the data annotation becomes even a bigger problem.
Yeah, so you can have it doesn't have to be a human. I agree, it's easy if you have a human, then you can directly go into the data and annotate it. You could have you basically take the annotated data points from this loop, and this would be like the only part of your data set that you have. For example, fraud detection, you run your product, you figure out that there's 10% of fraud. The 10% of fraud, you look at which IPs they came from, and then build basically this will be a feature into your model. So you wouldn't be able to look at the list of all IPs and then annotate which ones are fraudulent and which ones aren't. But that's kind of, in that case, I think it's necessary just to kickstart the loop.
Okay. Let's have a question back there.
Thank you for a great talk. I have a question about infra part, a very simple one. Because you're using TensorFlow, have you already tried out DF extended as well?
Is that in 2.0 or what do you mean?
Yeah, they basically just
Can you describe what it does? I haven't looked into it.
It's a full pipeline from TensorFlow that they just released last month.
No, we haven't looked into it. But one point of why so TensorFlow is, I guess the pipeline also accommodates for classical algorithms, I suppose. It's not just about the neural network. It's not specific to here is your network, here are the weights, and now run it through the test. It's not only about that, I suppose. It's also here is a function that returns 0 every time, regardless of the input. You can test that as well. Is that true? Yes. Okay. So in that case, that will help. And you say 1 month ago, I should look into this. Another thing that goes into this is actually something that I think is nice, is that if you package your sort of the production services in the right way, you can directly, like a Docker image, for example, you can directly test the image against the data. So you can have, for the tagged image version, which will be static or will be sort of defined, this was the version, you can have a score at that time, like how good was that version, and you can have a history. So it's kind of like versioning the performance metrics on top of the Docker images. So if you're clever about the way you wrap your services, then it makes it easier for you as well to test things. But a good point. I will look into it.
Thank you as well.
One final comment to your point that what happens if a human can't see to kind of annotate the data? I think.
Harder problem then.
Yeah, but I think it actually, one of the problems might be then maybe you're not looking at the right visualization of the data. In a sense, well, I'm not trying to argue with you. I'm just kind of pointing it out that, like, if you take pixel intensities, give them to people as numbers, it's useless. So you figured out that kind of showing them as colors is useful. So it's.
But I mean, there must be some sort of feedback loop. Like the fraud case, if you have never seen any fraud, then it's kind of hard to build a classifier that classifies fraud from non-fraud, right? So there must be some sort of feedback loop, and whether it's direct by a human's eyes looking at it, or sort of goes through the whole product loop, and then from here you can figure out maybe 3 months later whether the payment was actually fraudulent, which is a common thing in e-commerce. And then you can put it back into your data set where you build your fraud models.
Okay, just a quick comment, or maybe you can comment my comment. Connecting two presentations from Pipedrive, and they comment with this experience from machine learning was they estimated the churn rate, how many customers will leave during months, and they get with machine learning more than 90% accuracy. And very happy. And then they found out that the percentage is so high because all customers leave at the end of the month where no to pay. So after they fix this actually right data, then they also got good percentage of churn rate. But still, it was example how machine learning could be completely wrong. And especially if it's very good result, then you must be a little bit scared.
Yeah, I mean, I think this is the more general problem here that also came through a lot of the questions for Christian's presentation was overfitting. And machine learning is especially prone to overfitting. If you have a relatively small amount of data in a powerful model, you will fit to the data. It will fit itself to the data, or your optimization algorithm will fit it to the data, and you sort of have to balance between learning the sort of right generalization. If it doesn't generalize well enough, if you're sort of fitting only to these data points, then you're overfitting. I mean, this is a machine learning course from Mandarin G. There's no point in repeating it here. But basically, it can also happen for the sort of software 1.0 or below 2.0, basically. Because if you have even 10 data points and you're fitting one parameter there manually, like just looking at the visualization of the result, you can also overfit there. So this problem will always be there, and it's not machine learning specific. It's specific to you trying to optimize against the set of data, basically, and you need to be mindful of that as well.
But thank you very much, Taivo.
Right then.
Maybe we can see you in the discussion groups with this topic in between someplace and carry on the conversation there.
Right now here, or in one?
I mean, somewhere in between the next meetup.
Definitely.
But yeah, thank you so much for coming, and let's do some networking now.